What's the first thing you ever learned about black holes? Do a Google search for black holes and I guarantee that you will find this statement. A black hole is an area of such immense gravity that nothing, not even light, can escape from it. It's the first thing people learn about black holes, and it really is everywhere. It's so common, in fact, that it has become received wisdom, passed from person to person, with everybody repeating it but nobody actually questioning it. Is this the first thing you learned about black holes? If nothing else, is this all you know? If so, you're not alone. But why should anybody question it if indeed a black hole is, according to what has become a mantra, an area of space whose gravity is so strong not even light can escape? They should question it because it just happens to be wrong. Okay, not completely wrong, but exceptionally misleading. And to understand why, let's step back a bit. If you dig a little deeper, it's also often said that light cannot escape from a black hole because at the event horizon the escape velocity reaches the speed of light, and because light cannot travel faster than, well, light, then it cannot escape. This is not correct either. All of this leads many people to see gravity as somehow being so strong it pulls a photon back as if it were attached to a rubber band which is stretched to its full extent before the photon can leave the black hole. Gravity therefore acts like some sort of brake on photons attempting to pass through the event horizon into the space beyond, but this is not what happens. There's another piece of received wisdom which says that light only and always travels in straight lines. Unlike the black hole mantra, our own experience, or experiments we might have done at school, dictates that this one is totally correct and can be relied upon. Until, of course, we start talking about gravitational lensing. Here's an illustration of gravitational lensing from the European Space Agency. In this graphic at top left we have a distant pulsar, a type of rotating neutron star. In the centre we have a galaxy, and bottom right we have the Earth. The galaxy is obviously between the pulsar and the Earth. In this interpretation, light leaves the distant pulsar and is deflected by the mass of the galaxy in the middle of the image. Or to be more exact, the galaxy's huge gravity splits the light into two separate paths, meaning that we see two images of the pulsar from the Earth. Now this phenomenon is well observed and understood and gives us such things as Einstein crosses, which consist of multiple images of distant galaxies as shown in the inset at top right. Here we see some of the foreground lensing galaxy which is bending the light from a more distant galaxy into 5 separate images. But wait a moment, light only travels in straight lines, so how can its path be bent by gravity? And so we finally get to the answers to these questions. The path of light is not being bent or deflected by gravity. It can only travel in straight lines, as we said. It's space itself which is curved by gravity, as stated by Einstein. And because the space the light travels through is curved, the light has no option but to follow that curve. It's like a ball in a roulette wheel. It travels in a straight line, but the space in which it's moving is curved, so the ball has no option but to travel in a circular path. The more the mass, the stronger the gravity and the greater the curvature of space. Now, what do you think would happen in a place where the gravity is so strong, space is curved to extremes? That place, of course, is a black hole, where the physical laws we are familiar with are pushed to their limits. Here you have photons inside a black hole. The space they are travelling through has been warped and bent so much by gravity that the photons can only follow circular paths inside the event horizon. From the photon's point of view, it is moving in a straight line, but the curvature of space is so extreme that it leads the photon on a path which means it can never cross the event horizon. And this is the reason light cannot escape from a black hole. It's not directly to do with gravity or escape velocities, it's more a question of geometry, the geometry of extremely curved space-time, which imprisons photons forever inside a black hole. The extreme bending of space can also be seen in this simulation of a black hole by NASA's Goddard Space Flight Center. It must be stressed that all of this simulation is taken directly from Einstein's equations of general relativity and is not just some random guess. The simulation is, as far as it's possible to tell, an accurate depiction of what happens to light around a black hole as a result of the extreme bending of space-time. Seen edge-on, notice that the black hole's accretion disk appears to flow above and below the event horizon. It doesn't, of course. Space is curved so much in the vicinity of the black hole that light is, again, following a curved path, allowing us to see the part of the accretion disk which is behind the black hole. Watch what happens as the simulation changes to a full-on view and back again, and you will see the effect which curved space-time has on the light travelling through it. Another myth about black holes concerns how they consume matter. Supermassive black holes do not, contrary to what many people seem to believe, swallow their host galaxy. Stellar mass black holes do not wander the universe gobbling up everything in their path. This misconception arises from not understanding how gravity works. Let's investigate. Let me ask you a question. Which has the stronger gravity, a star of 10 solar masses or a black hole of 10 solar masses? Just think about that for a moment. The answer, of course, is neither. Their gravitational fields are of exactly the same strength. Why is this? The only factor governing the strength of a gravitational field is the mass of the object. Objects sharing the same mass will always have the same gravity, and it doesn't matter if one of those objects is a black hole, a star, or anything else. The only thing which matters is the amount of mass. Now let's give our 10 solar mass star a few planets. What do you think will happen to those planets if we replace the star with our 10 solar mass black hole? The answer is, of course, nothing. The planets continue in their orbits unaffected, although pretty soon it's going to get very dark and cold on those planets. But the important thing is that they are still orbiting a 10 solar mass body, so the black hole's gravitational effect on the planets will be no different from the stars. They will continue to orbit the black hole as if nothing had happened. Now let's place the black hole at the centre of a galaxy. Its gravitational influence is strong enough to keep planets circling it, but does not extend further. Remember, this is a 10 solar mass black hole which replaced our 10 solar mass star, so its gravity is no stronger than the star's was. It certainly cannot swallow anything further out in the galaxy. In practice, of course, supermassive black holes at the centres of galaxies can be measured in millions or even billions of solar masses, but the idea is the same. The gravity of the black hole has a finite range which depends solely on its mass. This amazing animation from the European Southern Observatory, compiled from 16 years of infrared observations, shows the movement of stars around the supermassive black hole known as Sagittarius A star at the centre of our galaxy. All of the stars in this animation orbit an unseen, compact object with around 4 million times the mass of our Sun. That mass obviously generates a strong gravitational field, but exactly how strong? So here's a question for you. How many stars in total do you think orbit Sagittarius A star? Bear in mind that there are approximately 1,600 stars per cubic light year at the centre of the galaxy, so how many have actually been pulled into orbit around the black hole? I'll give you a second to think about that. The answer is probably not as many as you might suppose. Only a few thousand stars at the centre of the galaxy orbit Sagittarius A star. even with its mass of 4 million suns, a few thousand out of the estimated 200 billion stars in the Milky Way galaxy. Therefore, contrary to popular belief, Sagittarius A star is not going to swallow the galaxy, still less anything beyond our galaxy. Let's zoom in a bit. The bright star moving rapidly here is designated S2. You can see it looping around the black hole, each complete orbit taking 16 Earth years. At closest approach, it moves at a blistering 17 million kilometers per hour and comes to within 17 light hours of the black hole, or 4 times the Earth-Neptune distance. Yet still, Sagittarius A's gravity is not strong enough to swallow it, even though the star passes very, very close to it, astronomically speaking. In fact, we've never seen any stars being consumed by our local supermassive black hole. The stars orbiting it are simply too far away and moving too fast to be consumed, so please can we put the idea that black holes are consumers of galaxies to bed finally. Occasionally, however, the black hole does swallow lumps of material in the swirling accretion disk of matter surrounding it. This results in a bright flare across many wavelengths, infrared, X-ray, radio. The flash you see in the middle of the screen is one of these flares, which is the result of Sagittarius A star consuming a lump or a knot of material which is orbiting it. This allows us to see exactly where the black hole is, but more importantly, it confirms its existence. This animation conclusively, therefore, demonstrates that there really is a dark, compact, massive object at the centre of our galaxy. Related to this, there's another common misconception that our entire galaxy orbits around Sagittarius A star. Clearly, from what we have seen, it does not. Only a few thousand stars out of 200 billion orbit the black hole. Our galaxy orbits around its centre of gravity, which is, quite obviously, the centre of the galaxy, taking 225 million years to rotate once. So let's kill that myth too while we're at it. And this is it. Sagittarius A star, the supermassive black hole at the heart of our galaxy, as imaged by the Event Horizon Telescope, a global array of radio dishes which form a virtual telescope the size of the Earth. Swirling around it is the accretion disk. The dark area in the middle is not the black hole itself, but an area around it where there are no photons because any entering that area are immediately pulled in. As Sagittarius A star itself is black because it emits no radiation, as we've seen no photons of any wavelength can escape from inside the event horizon, it's forever invisible, but it's inside that dark area, perhaps occupying 1/10 of its diameter. Well, that brings us to the end of our video about myth-busting black holes. We do hope you've enjoyed it. If you know of any other common black hole myths or misconceptions, we'd be only too happy to address them in a future video. Describe them in the comments, and you can also, of course, ask any questions you may have in the comments too. Do have a look at What is a Black Hole, our video which introduces black holes, and the other videos on the channel, of course. From everybody at Space Odysseys, thank you for watching and goodbye.